Our first guest runs the robotics lab at Virginia Tech. He spends his life designing some of the world's most sophisticated robots. Please welcome Professor Dennis Hong.
Thanks. So, good evening. Thanks for having me. Again, my name is Dennis Hong. I'm a professor in mechanical engineering, and I'm the director of ROMELA, the Robotics and Mechanisms Laboratory at Virginia Tech. So, what do I do for a living? Well, as a professor, I teach. As a scientist, I get to do research. And also, as a director of our laboratory, I get the chance to work with probably the smartest, the hardest working group of students, the ROMELA graduate students and undergraduate students. But the most important thing is I get to build robots. How cool is that, right? So I truly believe that I have the coolest job in the world. Well, if you don't believe me, let me show you. I'll show you some of the cool robots that we developed. So the first robot I want to talk about is called Strider. It stands for Self-Excited Tripedal Dynamic Experimental Robot. So it is a robot that has 3 legs. Actually, you can see the robots over here. So this is a biologically inspired robot. But the thing is, Josh, have you seen anything in nature that has 3 legs?
A squid after I've eaten 5 legs off it.
All right, that's a good answer. But besides that, I haven't seen any animals in nature that has 3 legs. So why is this biologically inspired, and why are we trying to do this? But before that, let's look at pop culture. You probably know the H.G. Wells' War of the Worlds. For some of your video games fans, that's a famous game called Half-Life that they have these cool alien robots that have 3 legs. But I want to point out that our robot Strider does not walk anything like this. So how does it walk? So what you see over here is a dynamic simulation animation of Strider walking. So it walks in a very interesting way. It swings the leg between the 2 legs and catches the fall. Isn't that cool? And the body flips 180 degrees every time it takes a step. It's pretty neat. But why are we trying to do this? Well, because it's cool, yeah? But actually, there's a good reason why we're doing this. So we call this the concept of passive dynamic locomotion. We're not doing this joint position control that you see in regular robots, but rather using the built-in dynamics. It swings its leg. As a matter of fact, this, even though it has 3 legs, it's more close to human walking. You swing your leg, you catch the fall, stand up again, potential energy to kinetic energy, and potential energy. Thus, it's inspired by human bipedal walking. So that is Strider. So we don't have this yet, but this is the next step that we want to do. We want to fold up the legs, shoot it out, long-range motion, deploys its legs almost like Star Wars, and it lands with its long legs. Observe the shock. And then what you see over here, this yellow thing, this is not a death ray. Well, just want to show that if you have cameras, because it's tall, it's 1.8 meters tall, you can see over obstacles like bushes. So it's great for sensor deployment. So is it all animation and stuff? No, we actually have 2 prototypes. As you can see here, prototype number 1 and prototype number 2. One of the problems that we had with the early prototype number 1 is the top body was just too heavy. We had so many motors and gears and those kind of things, so it's too heavy. So for the second version, we came up with this ingenious mechanical solutions. We synthesized these mechanisms, and we got rid of all the motors, and with just a single motor, now we can align all the joints. And now the top body is light enough, so it's now walking in our lab. So this was our very first successful step. It's pretty cool. Still, it's a little bit unstable, so we still need to continue our work on Strider. So the second robot I want to talk about is called IMPASS, Intelligent Mobility Platform Actuated Spoke System. You can actually see our early prototype over here with a carbon fiber body. So this is an interesting new type of locomotion robot. It's a wheel-leg hybrid robot. So it's a rimless wheel or a spoked wheel, but the spoke individually moves in and out of the hub, as you can see. So it can rotate, but also moves in and out. So it's really a true leg-wheel hybrid. We're literally reinventing the wheel. So why are we trying to do this? Well, for example, if you have a rough terrain, it can, just by using the contact touch sensor on the foot, it can adapt to the changing terrain. In this case, it's trying to walk over this cushion. But if it encounters a really, really tall, difficult obstacle, in this case, we have a big obstacle more than 3 times of its nominal height, then it switches to this deliberate mode, and using the laser rangefinder and camera system, it senses the obstacle size and shape, and it does intelligent planning, and it actually controls the spoke, so it can actually surmount, go over these very, very challenging obstacles. You probably haven't seen anything like that out there. This is probably the highest mobility robot for application could be search and rescue missions, or on Mars, scientific exploration, anywhere that the wheels cannot go, this is probably going to be the perfect locomotion robot for those kind of situations. This robot is called Climber, cable-suspended limbed intelligent matching behavior robot. So I've been talking to a lot of scientists from NASA JPL, Jet Propulsion Laboratory in particular, and all the geologists and the scientists tell me that the really science-rich sites, the really interesting places are always at the cliff. But these Mars rovers cannot go down the cliff. So inspired by that, we decided to try to build a robot that can climb up cliffs. So if you think about a human climbing a cliff with a cable, that is exactly the concept. So what you see over here, this is our early prototype. So it has 3 legs. So autonomously tries to figure out where to put its foot. And when it figures out where to put its foot, the blessed place, then it does a real-time calculation, decides how much force to exert to the surface so it doesn't tip and doesn't slip. So after it does that, you can see the 3rd leg trying to find the surface to put its foot. And then it can free its 3rd leg, and then it's difficult to see, but there's a winch and a cable and can pull itself up. So that's how it climbs. The next robot is called Mars. We have a prototype over here. Unfortunately, Mars is now retired, so it's like a museum piece right now. It's based on the NASA JPL's Lemur 2 hexapod robot. So we use this robot for many different types of locomotion. So we develop our own omnidirectional walking algorithms, and we use it for many different types of locomotion. For example, how to walk over uneven terrain, or in this case, a little bit difficult to see, but this robot is trying to walk on the sand where we have different moisture content in the sand, or the sand grain size is different. The foot sinkage model changes, so it tries to adapt its gait to successfully walk over these type of very difficult terrain. Well, we also have a lot of fun with these robots. For example, as you can imagine, we have so many visitors coming to our lab. So when they come visit our lab, the robot walks up to the computer, and the robot does this. Hello, welcome to Virginia Tech. Welcome to Romeo, and types on the keyboard to welcome you. OK, so this is a little bit different type of robot. This robot is called whole skin locomotion. We also call it the amoeba robot. So this is a soft skin robot that has a very unique locomotion mechanism. You probably played with a toy called Water Wiggler, water worm, that you can actually buy at a toy store. So think of that. It's a everting mechanism. It turns itself inside out. So you can see over here, we store potential energy into the skin to make it move, or we use active tension cords to make it move forward and backward. And one interesting approach that we have is a chemically actuated version. So there's no motors, no electricity. Just by using chemistry, we can make these type of water wiggler robots move, just like magic. Isn't that cool? All right. That's called Chimera. This is a more recent project called Raphael, robotic air-powered hand with elastic ligaments. Probably noticed that all of our robots have cool acronyms. I learned that you need to have a cool acronym name to get all the research funding, but yeah. So this is a robotic hand. So there are a lot of really neat high-performance robotic hands out there on the market. The problem is that these robotic hands, they're tens of thousands of dollars. They're very, very expensive. So research laboratories can afford it, but we want to use these for prostheses applications. And for these to be successful as a product, of course, it needs to be affordable. So in this case, we try to come up with a different approach. So instead of using your expensive controllers and motors, let's use compressed air. So using compressed air, it can actually grasp very delicate objects like a light bulb or a raw egg, but also it can even crush an empty soda can just by changing the air pressure. So it's very effective, dexterous, and the best part, we caught that egg, by the way. The best part, the robot hand, the first prototype, cost only $200 to make.
Trigger the other fingers.
Right.
There we go.
OK, let's look at the next robot. OK, this next robot is called Hydrus. It's Hyper Degrees of Freedom Robotic Articulated Serpentine. It's actually a family of snake-type robots that does not only slithers, but it actually climbs up structures by wrapping itself up. Among the Hydrus robot, this one is particularly interesting. It's called Hydrus Arm. So we have a standard snake-type robot arm. But the cool thing is not the robot, but rather the user interface. As you can see, this black cord, that's a simple optical fiber. And this student, probably the first time using it, she just grasps it and just moves it. And the robot mimics the motion. So you can actually generate a lot of the type of complex motion. Again, first time using it, you can use this for doing complex operations. On the war zone, there's roadside bombs. Currently, they send out these packbot robots. It's very expensive to train an operator to do this. If you have something like this user interface is so intuitive, you just pick it up and start using it. It's called Hydra's Arm. Okay, this is another different type of project. This project is called the Blind Driver Challenge. Yes, I know what you're thinking. We have developed the world's very first and only vehicle that can be driven by a blind person. Yeah, before you say anything first, now I want to point out that this is not going to be an actual product. You're not going to see this on the road with other cars until it's proven safety. We had our first successful test run last summer. So it was sponsored by the National Federation of the Blind Jerningen Institute. Let me quickly show you some video clips of this. So again, this student is completely blind. We do work with the blind. It's not something that we just develop something in the lab and give it to the blind community. We closely work with them. So the vehicle is equipped with many different types of sensors, laser rangefinders, and camera systems. And the computer system builds a map around the vehicle called the world model that the computer can understand. And we developed this many different types of non-visual user interfaces that give real-time information, high bandwidth information to the driver who cannot see. You can see the big smile on her face. So we have a lot of interesting things happening with this project, so you're probably going to see a lot of new exciting things on the Blind Driver Challenge early next year. OK, this is currently our superstar robot called Darwin, dynamic anthropomorphic robot with intelligence. So as you know, I've been interested in human walking. So we started this project in 2004. At that time, this is something really new. So we didn't know if it is even possible. What kind of motors can you use? What kind of control scheme can you use? So this was more of a feasibility study. Thus, it didn't have any sensors, no feedback control. So for those who know about these kind of things, if you don't have any sensors, if there's any disturbances, you know what happens. Right? So in the following year, 2005, based on our really nice the feasibility study, we did the proper mechanical design and came up with Darwin 1 in 2005. And now it can stand up and walk. But still, notice that it still has this umbilical cord, so we're still using off-board computing and off-board power. So the following year, in 2006, now it's really time to have fun. So we give all the sensors it needs and all the computing power it needs, 1.5 gigahertz Pentium chip, 2 5-hour cameras, rate gyros, accelerometers, force torque sensor on the foot, lithium polymer batteries, and now Darwin robot is completely autonomous, meaning that you press start, nobody touches it. With this camera, looks around, it figures out where itself is, looks at the ball, looks for the goal. It's not tethered, nobody's controlling it, and it tries to play a game of soccer. Let's see how it does. Yeah. Yay! So why did we try to train it to play soccer? There is actually a competition called RoboCup. It's an international autonomous robot soccer competition. And the official goal of RoboCup is, by the year 2050, we want to have full-size humanoid robots play soccer against the human World Cup champions and win. It is a true official goal. It's an ambitious goal, but we believe that we can achieve this goal. So towards that goal, we're doing research and trying to develop these type of robots. So just to give you a feeling, this is 2 years ago in China, in RoboCup 2008. This is last year in Austria, last year RoboCup. You can probably see the pace and action. So these are not remote controlled, purely autonomous robots. You can see the real-time ball tracking. So it's thank you. So what you see over here, this is a beautiful crystal Louis Vuitton Cup trophy. This is what you win when you win the Best Humanoid Award. And for the very first time this year, we're planning to bring this trophy to the United States, so wish us luck. So Darwin Robot has a lot of other talents as well. 2 years ago, the Roanoke Symphony Orchestra visited Virginia Tech campus, and we had the holiday concert. guess who the guest conductor was? It was Darwin. As a matter of fact, Josh, would you like to meet Darwin?
Absolutely, I would. He's about as good at playing soccer as I am.
Yeah. So over here, this is Darwin 3. Now he's retired. Says hi. Hello, everybody.
Hey.
Yeah, it's bowing.
What is he doing? Oh, he's bowing. I thought he was doing something else.
I was doing some dancing. Oh, that's pretty cool. So, hey. So he used to play soccer, but now he retired, and I guess now he's a dancer.
Right.
Oops.
He's about as raunchy as most ex-soccer players, I think.
Very good. Yeah, so now he's our lab receptionist. So when people come in, he introduces other robots and gives everybody a lab tour.
Is he married?
Yeah. Oh, he's doing the robot, right?
Yeah. All right.
All right. Pretty cool. All right. Thank you, Darwin.
Oh, wow.
Yeah.
Very impressive.
Cool. All right, so this is the latest version. This is Darwin 4 Plus. It's much smarter, stronger, faster. And in this video clip, it's just trying to show off. I'm strong, I'm macho, right? I can even do like Jackie Chan, martial art movements. And it walks away. All right, so we brought some of our robots today, the soccer playing robots. I want to give you a quick demonstration. Now, these robots, these are not the Darwin series robot that we use for the Robocop for the autonomous robot soccer competition, but these are called bioloids, and we use these robots to train. There you go. We use these robots to train our humanoid robot Darwins for playing soccer.
Now, how is he doing what he's doing? Is he being directed by anyone from anywhere, or is he just doing this spontaneously?
So the autonomous robots, you'll be able to see it tomorrow. So tomorrow, if you come to the Washington Square Park tomorrow from 10 a.m. to 5 p.m., you'll be able to see our autonomous soccer playing robots. But these are currently just having...
So these ones are programmed. These ones know what they're going to do.
These are not fully autonomous. Oops.
Oh, lost the ball.
And this is why we don't use these for playing soccer.
Thank you.
Thank you.
Yeah.
Oops.
These these guys are great, Dennis, but I just don't think they're going to be beating Brazil anytime soon.
I don't think so. All right. I think that's enough. All right. Thank you. Thank you, bioloids.
Thank you.
Oh, thank you. Yeah, cool. All right, so, this robot is kind of interesting. This robot is called Charlie, Cognitive Humanoid Autonomous Robot with Learning Intelligence. I think this is the first time we're introducing to this to the general public. Charlie, as you can see, as I mentioned, by the year 2050, we want to have full-size humanoid robots playing soccer against the human World Cup champions. We're not kidding. This is our first attempt to do this. This is a 1.5-meter humanoid robot, completely autonomous, untethered, and it's the first of its kind in the United States. You probably know about, you've probably seen a robot called Asimo from Japan, Honda, right? Have you seen those robots, right? And in Korea, they have this humanoid robot called Hugo from Keist. Now, United States, now we have Charlie. So let me introduce Charlie. So this is Charlie over here. Mm-hmm. Let's wake him up. Hey, Charlie.
Wow, we have a large crowd today. Hello, everybody. My name is Charlie. Nice meeting you all.
Nice meeting you too. It's pretty cool. So unfortunately, today we were not able to bring the lower body because we're still working on the lower body in the lab. So we only have the upper body.
Oh, I knew they forgot something. Thanks, guys.
Yeah, sorry. So Charlie, what can you do?
I can walk like you with 2 legs. I can see and recognize objects with my 2 camera eyes. I can track objects and grasp them with my hand. And most of all, I can play a game of soccer.
There you go. So we're going to bring this guy this year to Singapore for RoboCup 2010. So it's going to be pretty cool. All right. All right, so this is a video clip. This is early this year, the first time I'm running Charlie. So the most interesting thing, the most remarkable thing is that we started this project only a year and a half ago with 12 students with a seed funding of only $20,000 with some donations of parts from companies. As you can see, it's completely untethered, bipedal walking. It might look simple, but this is something very, very challenging to do. And again, we're the very first group in the United States that we accomplished this with our students. So, very good. All right, so how did everything get started? Well, when I was a young kid, when I was 7 years old, I watched Star Wars for the very first time in the Man's Chinese Theater in Hollywood. I was completely blown away by all the cool, neat stuff, especially the interesting locomotion of R2-D2 and the human-robot interaction with C-3PO. So when I was a young kid, 7 years old, since then, I decided to become a robot scientist, and I'm here today. Right? So, okay. Well, that's it. So thank you very much. I would like to quickly introduce some of our students over here. So we have Blake, Taylor, and some other students. Taylor, Igor, Sean.
Dennis,
Thank you,
Dennis. Fantastic. Thanks, guys. Who here likes animals? Yeah. I mean, not to eat them, which is not nice, but like to play with them, to explore them, to figure out how they live and what they do. Our next, well, just imagine a job that is perfectly designed for anyone who loves animals, who loves getting wet, who loves doing experiments, who loves finding things out. The next scientist is a senior aquatic biologist at the California Academy of Sciences. She spends most of her time with a particularly charismatic colony of African penguins. Please welcome Dr. Pamela Schaller. Hey.
Thank you. Let me just start with, I was sitting listening to people do what I was doing a long time ago. So I was in the seats where you guys were. You can do what I'm doing. Study science, study math, learn as much as you can about animals. My job, I'm so excited about sharing my job with you. This is what I do. Half of my day, I'm in a wetsuit. It's fantastic. This is a baby shark. See how big it is? This thing is only about a month old. The female gave birth while she was with me. And the way that it works is sharks give birth, they lay eggs, or they give live birth. And you're going to see in the next show, probably 1 or 2 slides, you're going to see how a shark actually gives birth. I dive with octopuses, or octopi, depending on who you're listening to. What I'm trying to do here is just examine her arms. This is a female. And what I'm also trying to do is just interact with her. So I'd get underneath the water. This is a very large tank that we had. It was supposed to represent the Farallones Islands. It's an island off the coast of California. This is a giant Pacific octopus, and one of my most favorite interactions. So this is a pelagic ray. This ray, we want it to move. That's a sling. That's what we call those things. You put the ray in the sling in order to move it. What we're doing here is we're actually ultrasounding this ray. And what we want to make sure, if we're moving animals, because some animals can be pregnant, we want to make sure if we're moving them and they are pregnant that we allow for the extra care for its offspring. So that's what we're doing. You can see in the very center down here, there's a doctor, and what he's doing, he's pretty much just has that same thing that we use on humans to be able to determine how well the offspring is developing within ourselves. It's the same opportunity for us to be able to take a look inside of this animal. So this is a shark giving birth. In the upper left-hand corner, that is what a pregnant shark looks like. So just how humans get these big bellies when they start getting into 7, 8, 9 months of pregnancy, it takes about 13 to 14 months for this animal to give birth. And it's not actually, they're not giving birth the whole time. They've got, that would be a really long time. And that's actually one of the offspring that has come out of her. In the upper right-hand corner, you can see it's upside, when they give birth, the babies are, and they're basically upside down, and their bellies are close to the mom's belly. And they come out swimming right away. They need to start feeding right away. The mom, after they give birth, the mom pretty much just leaves. So they need to be self-sufficient. So that's why they're so large when they're born, because they need to be self-sufficient. So I know. This is what I am so honored and privileged to do. I can't even tell you. Lower right-hand corner, that penguin chick, that is not even 24 hours old. And I oftentimes get to see them hatching out from their eggs. It takes about 2 days for it to come completely out. And sometimes when I'm checking on the egg, there's this little beak at the little hole, and it talks. It starts to call already. Even while it's inside of its egg, it starts to talk already. And this is a really good example of what a penguin chick, a healthy penguin chick should look like. You take a look at the feet, you see how nice and puffy they are. They should be really well hydrated. And if you can take a look down towards the bottom here, they're attached inside of the egg through something that's basically like an umbilical cord. There's blood vessels that go inside of that egg. And that's how the chick develops. It's feeding off of what's inside of that egg. So when they come out, we always keep checking and make sure that that area starts to heal up really well. And within 24 hours, you can see already that it's got a little scab on it. Upper right-hand corner, those are 2 penguin chicks. They were brother and sister. They're still with me today. Fantastic. Both of them are really fun birds to work with. What I'm doing is I'm hand raising those birds. At some point, usually around 3 or 4 weeks old, sometimes I need to step in and do some hand raising with them. They do get somewhat imprinted on us, but it's at some point, usually when they're about 2 or 3 years old, they begin to find a mate, a significant other, and they live together for the rest of their lives, and I just become kind of a third party to the relationship. And then the upper left-hand corner, that is another one of those white-tip reef sharks. So I've had the privilege to build 2 buildings full of animals. I've brought animals into new places. I've had to design exhibits. This is one of the processes in terms of being able to build a place. You have to think about everything. You have to think about where would penguin chicks be? Would it be safe for them? Where would adults be? Where would it be safe for them? Where would geriatric penguins, where would they live? We want them all to live together, but there's a lot of challenges with each of those. The exhibit that we built is supposed to represent South Africa. It's supposed to represent Boulders Beach. This is me testing the exhibit out. One thing you're going to notice on the upper left-hand corner, you see how there's like these white panels, and you see people kind of peeking through them. This was me testing the exhibit out. I have on scuba gear just in case, because I designed this exhibit, I'm concerned about every aspect of it. And I'm bringing birds in for the first time. Number 1, I don't want them to run into the glass, not realize that the glass is right there. Number 2, I want to make sure that they can navigate around the pool. The lower right-hand corner, that's just pretty much, I just have to watch these penguins and make sure they get in and out of everything that I want them to. Upper right-hand corner, I've been lucky enough for 5 years in a row to study these penguins, their behavior. You take a look, you see A, B, C, and D. What I did was I spread the exhibit out, put it into quadrants, put it into 4 parts, and pretty much just looked at the penguins and how much time they spent in each quadrant to let me know, are they utilizing the entire exhibit? This is what the exhibit looks like. See, it's really kind of exciting to be from that cement part and that testing part to be this part. These middle rocks down here, one of the things that I felt was really important was to be able to feed the penguins while they're swimming, because that's what they would normally do in the wild. This allows me to be able to stand on this rock work and then feed the penguins. And we'll show you a video of that in a little bit. All that I do and everything that I have to do, it can be stressful. I can be very nervous about it, especially because I'm dealing with animal lives. dealing with reproduction. I could be moving animals. On the upper left-hand corner, that is me moving some very, very, very large sharks. It's hard to tell, but that animal was bigger than me and weighed probably my weight plus a half. So 250 pounds or so, 225 pounds. First of all, I have to get that animal into this container. So it's not like I can just be like with a little net and throw it into a container. I actually had to get into a tank with a tank on my back, with a regulator in my mouth, and swim after this animal and grab a hold of the pectoral fins, the fins on the side, and steer him around until he got into a sling. And then that sling had to get carried. You see how large that sling is? That sling had to get carried by 8 people total. That's how heavy that animal was. Put it in this container, and eventually drove this animal all the way to Denver. And one of the funniest things, so I'm in Nevada, and I pull up to go get gas in a truck, and I've got these sharks. There's 2 of them. Eventually, there's 2 of them in there. I have these sharks in the back of the truck, and these guys pull up next to me, and they've got horses in the back of their truck, right? And they obviously, because the truck looked so unique, they wanted to know what was in there, and I said sharks. And the guys walked away from me, and then it registered, and they turned and they looked at me, and they were like, "Are you serious?" I'm like, "Yeah, I'm driving sharks across the country. It's my job." Lower right-hand corner, Good Morning America came on, did some weather in the penguin exhibit. No. Yeah. This is mostly lately what I've been known for. This is a penguin wetsuit. I'm just going to put this down for a minute. I am not in the habit of putting clothes on animals. However, can you see his head and his tail, just how exposed it is? Can you see? You see how bald he is? He didn't really have much feathers on him at all. Penguins use feathers for insulation. It's required for them to be able to swim and stay warm. And this bird, he's supposed to replace his feathers every year and did not. And I ran out of options with him. I tried heaters, we tried medication, and nothing worked on him. And this is my creation. It's a little penguin wetsuit. Yeah. What's really exciting is I get to see this bird every day. His name's Pierre, and he's got feathers now. He grew his feathers back, and it's just, that's something that you never know when an idea is going to come to you. It just did. And I'm so honored. They wrote a children's story about it. And it is really, Jean Marzullo, I know, she's the one that does the I Spy books. She is fabulous. The illustrator did a fabulous job. People now recognize me because of this book. And she'll be at Author's Alley tomorrow, I think right around 1, something, yeah. And she'll be there to sign the books, and the books will be there. And she'll also be reading the book. And again, I can't believe I've given the honor to be recognized in a children's story. And Pierre is still alive, and he looks great. He really looks very, very good, the best I've seen him. So we've got some videos for you, a couple of them. You want to start with the first one? This is Osio. Osio has these big white cheek patches. African penguins are not usually known for that. They usually just have white stripes. What he's about to do is emit a sound. It's called a bray. Now, we don't have the sound, but it sounds like a donkey. And the males especially, and this is a male. So you don't even really need the sound to see how much effort they go through. When the males make that sound, other males will basically what they're doing is that's their territory, and they're letting other males know that that's their territory. So you can go to the next one. This is my job. So that exhibit that you saw, this is what I'm doing. I have a headset on every day, twice a day. I'm in a wetsuit twice a day. I'm feeding the penguins twice a day, and I'm talking about it. I'm educating people. For me, it is a very rewarding job, but the responsibility in having these animals in captivity is that I educate about their lives, and I get to share my life with them and theirs with me. And it's a really exciting, enticing thing. So I'm trying to hand feed these birds as individuals, and I have to keep track of every fish that comes out of that bucket and goes into a penguin's mouth. So I'm talking to the public, I'm answering questions, I'm keeping track of what every penguin in there is feeding, and I'm trying not to fall off those rocks that I showed you. So you balance a lot of things. It's a very dynamic job, and it has a huge, as I said, a huge amount of responsibility with it. Yes, it's fun and exciting and cool.
Now, Pam, when you say that you're keeping track of all the fish that you're feeding, you can tell all of the penguins apart.
Right.
To us, they just look like penguins.
Right.
To you, they're actual, they're individuals, right?
Right, absolutely. And
And how do you tell? Is it always markings on their skin? How can you always tell?
There's a number of things. The faces look different to me now. So some of the faces are longer, some are wider. Their beaks are all a little bit different.
I guess they all are. I guess it's probably like a penguin asking another penguin how they can tell the difference between people, right? Like,
Right.
well, we all look different. If you know what to look for. I don't know what to look for in a penguin.
What I look for is the markings for sure. Also behavior. So it's an animal that always consistently comes towards me, goes away from me, how they interact with each other. They look completely different.
And in that video, some of the dudes were just hanging out upstairs.
Yeah.
Why aren't they wanting food?
They don't listen to me.
Yeah, but you have food.
Right, I know, I have food. The bird on the right-hand side was replacing his feathers. All penguins are supposed to replace their feathers once a year, which Pierre did not, which is why he wore the wetsuit. He's replacing his feathers. They don't swim when they're replacing feathers. That's number one. And then there's a bird up there, and it happens to be Pierre, too. He's been very significant in my life in terms of responsibility. I was on a surgeon's table, a veterinarian, and talk about this. This is really fun. He had cataract surgery. So his vision is somewhat limited, even post-surgery.
You give the penguins cataract surgery?
Surgery, yeah.
My grandmother couldn't even get cataract surgery.
I know, and people are so amazed. Yes, I've been in MRIs with penguins for lower back pain. And you know what?
How do they communicate that they have lower back pain?
That is the hardest thing. Feel my back hurts. That is the hardest thing about my job.
Do they bray like that?
No. He was beginning to, that particular bird was not walking normally anymore. And it progressed to a point.
So he came up to you and pointed his little fin at
I know,
his back.
it's like, this is... So in terms of the cataract surgery, so I walk into the veterinarian who does it, and she mostly does cats and dogs, and she has her regular patients in there. So I'm walking in with this penguin, and there's all these people, these cats and dogs around, and they just couldn't believe their eyes. And it had to continue to keep going for updates with the veterinarian. Same thing. Every time I'm in there, I'm like walking around with this penguin in my hand, and it's pretty funny. Imagine being in a veterinarian's office and a penguin walking by you.
That sounds like the setup to a joke. Ladies and gentlemen, please thank Pam. Thank you. Gazed at the night sky and had a wistful moment where you think to yourself, is there anyone out there gazing back at us from some distant planet somewhere? The question of whether or not there is intelligent life on other planets is people have wondered about this for so long. It's a philosophical question, it's a religious question, and it's fundamentally a scientific question, as I think almost all questions ultimately are. And our next guest has devoted her life to really being at the cutting edge of looking into this question and rigorously analyzing it. She's one of the world's foremost experts in the field. Please welcome Jill Tarter.
Hello, Josh. Well, I'd ask how many of you had seen the film Contact, but I couldn't see your hands if you put them up. So let me just start by saying that I am not Jodie Foster. I do, however, get to do the job that her character, Ellie Arroway, did in the movie Contact. However, I don't wear headphones except for really cheesy Halloween costumes, right? My computers do the job of searching for signals, looking for patterns in noise that could be generated by a signal that was engineered rather than a signal that was produced by nature. This might be a way of finding out whether there are any other technological civilizations out there. I love what I do. I'm never going to get very rich at it, but my life is very rich indeed. I get to spend every day trying to figure out puzzles, trying to answer questions that I've asked, actually humanity has asked for thousands of years. And sometimes I get some answers. Sometimes I figure out things that no one else has yet figured out. And so it's a very rich life indeed. And while I may never have a great big corner office on Wall Street, I in fact do have some pretty spectacular scenery in my job. This is the world's largest radio telescope on the island of Puerto Rico. It's a big sinkhole. It's a big 1,000-foot hole that's lined with metal panels, and 500 feet above it, there's a superstructure with receivers that capture the radio waves. And I got to sit out on the cables, these big bridge strands that hold up this superstructure. So I'll trade that for a Wall Street corner office any day at all. I work with radio telescopes. Now, I suspect most of you are more familiar and have probably looked through an optical telescope. So optical, radio, they're just different parts of the electromagnetic spectrum. Waves, okay? Optical waves are really short. Cram a few million of them in a meter. And radio waves are much longer. A few hundred would fit in a meter for the shortest radio waves, and some radio waves are many meters long. All the same stuff, carrying information, just different frequencies.
And Jill, sorry to interrupt, but just because there are quite a lot of young people, can you just take us through what are radio waves and where do they come from originally, and why can't we see them?
That's a good point. We can't see them because our eyes aren't sensitive. Our eye is a very small receptor, and it's not going to be able to capture a wave that's that long. Where do they come from? Well, basically, different kinds of sources in the universe emit different radiation, different wavelengths of radiation. The short radio waves, the optical waves, or even shorter, X-rays or gamma rays, basically are telling us about places in the universe that are hot, like a star. The radio waves, the long waves, are produced in places where it's pretty cold. So we learn different physics when we use these different wavelengths. And of course, until very recently, our view of the universe was limited to what we could see with our eyes. We then began to expand a little bit into the infrared, and in the middle of the last century, mainly as a result of radar innovations during the Second World War, we developed radio telescopes. Now, let me illustrate what the universe looks like in these different wavelengths. Looks very different. We live in a galaxy that's called the Milky Way galaxy. If we could step out of our galaxy, which has about 400 billion stars, we could step back and look at it from a distance, it would look something like this. This is our nearest neighbor galaxy called Andromeda, or M31 by the astronomers. And this is what that galaxy looks like if you use a big radio telescope. And you can see all the bright light there. Those are all stars shining. And there are a lot of stars at the center of the galaxy, so it's very bright there. But what does that galaxy look like in the radio? What if your eyes could see radio? Well, if you looked at a particular frequency where hydrogen gas emits, that's the same galaxy. Doesn't look at all the same, does it? Because you're looking at different things. You're not looking at the bright stars. You're looking at this neutral hydrogen gas. And hydrogen is the most abundant element in the universe. So it's important to study hydrogen. And you can see that it's dark in the middle, whereas back here, it was bright in the middle. The reason is that those bright, hot stars ionize. They change the hydrogen neutral gas, and you can't see it. It isn't there in the center because of the bright stars. So we learn a lot of different things about the universe by doing our observations in different wavelength bands. And in particular, we think the radio is a good place to look for engineered signals because radio waves travel throughout the galaxy. If you were a light ray or a radio ray, it would take you, traveling at the speed of light, 100,000 years to go from one end of the galaxy to the other. So that galaxy is about 100,000 light years across. I want to look at stars not in Andromeda. They're very far away. Any kind of transmitter there would have to be incredibly strong if I were going to detect it. I want to look at stars in our own Milky Way. And in some directions on the sky, when I look, there are stars in the Milky Way in the foreground. Here. Okay, that's Andromeda. We're looking in that direction, but in our own Milky Way, those star symbols and the 3 white dots, those are stars that are like our sun, very nearby, and I'd like to study those. So we've built a telescope that can do this at the same time. My astronomy colleagues can look at distant objects, and I can look at nearby stars in the foreground. That telescope looks like this today. There are 42 small dishes that reflect radio waves, and we hooked them together with a lot of computing power as if they were one great big giant telescope. Now we have 42 today. We're just hoping that someone will add money and it'll grow to 350 because that's our goal. But we're using these telescopes today to do a search for extraterrestrial intelligence at radio frequencies. At the same time, the astronomers that I work with are studying the more distant universe in radio waves. And some of my colleagues are actually using optical telescopes looking for different kinds of signals. Now, inside, if you were sort of to look under the hood of one of these telescopes, there's this really strange looking device. It always reminds me of sort of early Buck Rogers, zzz, 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 right? Death ray kinds of things. But that's like the aerial on your car. The mirrors of the radio telescope focus the radiation down on this device. And we receive a very wide range of radio frequencies. The big spiky things, right, they pick up longer radio waves. And the small spiky things, they pick up shorter radio waves. And we can observe all of these at the same time. Now, what in the world, I've been talking now for 10 minutes, what in the world am I talking for? What are we looking at? What would a signal, an engineered signal from someone else look like? Well, here's a picture. All right? There's a signal in there. This picture is displaying frequency this way and time that way. And the signal that's in that picture is coming from the most distant human object. It's the Voyager 1 spacecraft that is now 106 times as far away from us as the sun is. It's about to leave the solar system and travel off into the interstellar medium. Have you found the signal yet? Does anybody see it? Does that help? Our computers have no trouble whatsoever finding that signal. Once we can tell a computer the kinds of patterns to look for, maybe someday we can make our computers sing and dance like these wonderful objects. But once you can tell the computer what you're looking for, it can do a really good job at finding a pattern. So this is what an artificial signal would look like. What would it sound like? There should be an audio file. Right. What's that? What is that? That's actually noise. There's nothing there. What about that? Can you hear it? That's an artificial signal like this one. We don't tend to use audio recordings or our ears to detect signals because we only are sensitive to a very small range of frequencies. And there's a lot of information that we want to cover. But I've already told you that when you can define what you want to look for in the noise, computers do a really good job. But what about signals that you can't define yet? What about anomalous kinds of things? You don't know enough about them to program a computer to find them. Well, what's good at finding patterns in noise? Well, you are. Your brain and your eyes, particularly, are really good pattern detectors. And so last year I was given a prize by the TED organization and given a wish, the ability to make a wish to change the world that TED would try and make come true. And I said I wanted TED to help me enable Earthlings everywhere on the planet to become active participants in this search for cosmic company. So we are starting a community that we call SETI-Quest. So look us up at setiquest.org. We're trying to find ways that a number of different individuals can participate in making the search better. So we could use some of those Virginia Tech really bright students to help us write better algorithms for finding different kinds of signals. And we can use you as citizen scientists to help us look at data and find anomalies that we're not yet aware of. So I love the job that I do. And one of the things that excites me about doing this work is that I think even if we do not ever find a signal, SETI can change the world. Because the act of looking for intelligent signals from a distant technology opens up our horizons, makes us think about ourselves in a much larger environment, a more cosmic perspective. It holds up a mirror and says, hey, you there on Earth, you're all the same. I think the idea of thinking about whether there are technologies elsewhere helps to trivialize the differences among us that we find so difficult to deal with. That's why I get out of bed every morning. That's why I work on SETI. So I'm going to end by showing you some images of the telescope as we hope it will become and as it is today. And I'd ask you to think about joining in this search, supporting it as a benefactor or as a citizen scientist or as someone who's eager to tell the story about looking for life elsewhere to your friends and getting them involved. Because this may be a search that lasts for generations before it succeeds. And I am always in search of my replacement and the future generations to carry on this really cool job. Thank you.
Thank you. You know, whenever we study animals, or whenever we build robots, whenever we search for intelligence in outer space, what we're ultimately doing, we're dealing with the brain. We're dealing with thought. We're dealing with consciousness. Every thought you ever had took place within the walls of your head. I mean, even if you believe that the thoughts exist somewhere else, at least the way that they show up is in electrical impulses in your brain. If we can know more about that, then we can know more about what it means to be human. And our next guest has devoted his life to that question. Please welcome Professor André Fenton. André.
So good evening. It turns out that I have a cool job. In fact, I have to thank you and the organizers for inviting me here because I'd never thought that I had a cool job. And struggling with trying to come up with what to explain about my cool job, I asked myself and my family and friends what was cool about my job. And I got a very, very long list of cool things about my job. And I decided to tell you about 3 of them. Okay? 3 cool things about my job. The first thing I'm going to tell you about my job is that I get every day to work on something that I have always been interested in, forever, as far as I remember. And that thing is me. Okay? Okay? So every day, I get to work and I get to recruit other people to work on working out what it is that helps me become me, what makes me me, and that is understanding how my brain works. Okay. I'm going to show you in a moment an example of one of the things that fascinated me early on. There are varieties of illusions that you can observe. Here's one of them. I'm going to ask you whether A is darker than B. Okay? Does A look darker than B? Okay. Well, A sure looks darker than B to me. It does work out, however, that they are indeed the same. Okay? We can demonstrate that by drawing some bars that are the same color as A and B. And the reason that A looks darker than B is an illusion that comes from an understanding of how the eye and the brain processes the information that you see. Okay? And I won't go into the details of that, but what is very clear to me when I saw illusions like this early in my life was that it was not certain what was real, and that what was real had a lot to do with my brain. So I always became fascinated with the notion of subjective reality, that my brain in some way is interpreting the world and making sense of the world in a way that's perhaps unique to me, or at least unique to my species. I'll give you an example of the kinds of things that I study in a moment. So one of the jobs of a scientist, in fact, the main job of any scientist, whether you're a neuroscientist as I am, or a physicist or a biologist, the main job of a scientist is to find solvable problems to work on. Okay? So I'm interested in understanding my brain. I'm interested in understanding a particular set of features about my brain, that being how I think. Okay? And that's a very complicated question to even pose. In fact, let me tell you a little bit about the brain. Okay? There are about 100 billion neurons in the typical human brain. That's a very, very large number of neurons. Neurons are the individual cells that make up a brain. Okay? Those neurons, each one of them, on average, makes about 10,000 connections to other neurons. So we have trillions of connections in the brain between neurons. And one of the fundamental things that neurons do is communicate with each other across these connections. These connections are called synapses. And we've been able to work out how the brain stores information in memory by changing the connections between those neurons. And that's one of the areas of research that I've particularly fond of and have had some success. We've identified a single molecule and how that single molecule operates to store the information that you're going to collect from this experience, from every experience that you've had. And if you're going to keep that information, if you're going to store those memories for your lifetime, you're activating this molecule PKM zeta. The way this molecule works has taught us that it's possible to erase memories, it's possible to enhance memories, and it hopefully will teach us how we might interfere with pathological memories, as in traumatic memory disorders and the like. Okay? But I have a different question that my laboratory also works on, and that's what I'd like to share with you today. I've always been fascinated, okay, by the fact that my brain changes, and I learn from experience. Okay? And what I learn will inform how I will subsequently experience the world. Okay? That's the neat thing about brains. They're plastic. As you experience the world, as you listen to the various talks today, your brain is changing, and it's changing for good. And you are now a different person, and you will experience the world differently as a result of that. So that was the thing that our laboratory would like to understand. How is it that our brains interpret the world in the multiple ways that we can interpret the world, and in the ways that are determined through experience? So I'll give you an example of that. I'm going to ask you to do what is known as the Stroop test. Okay? I'm going to show you a bunch of words, and I'm going to ask you to say the color and ignore the meaning of the word. So here the right answer would be black. Okay? And I'm going to ask everybody to call out, okay, the color of the words that I'm going to show you. Okay, are we all ready? Okay, the monitor will say ready, go, and about every 1 second you'll get a new stimulus. Okay? This is a psychological test, and it will tell me enormous amounts about my audience. Okay? Are you ready? Okay? It will say ready, go, and then begin. Okay.
These guys are good. These guys are good.
So, did anyone recognize the Turkish words? Okay. So, those of you who don't know Turkish didn't have difficulty calling out the colors of those Turkish words that were color incongruent. Okay? Color incongruent is the type of word that you had difficulty with. So when red was written in the color blue, you had difficulty to call out blue because your brain had two interpretations of that, and it had to choose one or the other. Okay? It had to choose one or the other. Okay? And so that very simple problem that we just demonstrated should have given you a sense that there is a difficulty in making sense of the world when you have to make choices between your interpretations of the world. And those choices are sometimes dictated by your experience. Those of you who have not experienced Turkish didn't have as much difficulty as those of you who have experienced and learned English. So we wanted to study this in the rat. Okay? And what we did, I'm going to skip through this quickly, what we did was we created a situation where a rat was on a carousel, very much like the carousel you could go to in an amusement park. And when the carousel turns, the rat can understand where it is, color-coded red here, in the room, like in the amusement park, okay, whether it's in the north or the south or near the fountain or far from the fountain. It could also understand where it was on the rotating arena relative to the smells on the arena that the rat cares about. So very analogous to you being on a carousel, knowing where you are relative to the red horse or the black horse, that kind of thing. And what we are able to do is record the activity of the rat's brain, the electrical activity of the rat's brain, because that's one of the neat things about a brain. It's very much like a heart. Okay? The brain makes these signals and communicates by sending electrical pulses across those synapses amongst the 100 billion or so neurons in the brain. And if we were able to record 20 or 30 of these neurons, and by putting that information into our computer and teaching the computer how to decode the activity of this rat's brain, we could, in essence, mind read the rat, and we could see that the rat was sometimes thinking about where it was in the room and sometimes thinking about where it was on the rotating surface. And we could do that reliably in a variety of situations. I would love to demonstrate that to you here, but there are difficulties with bringing rats in and recording their electrical activity up on stage. But I am going to show you in a few minutes a recording from a colleague of mine. Now let me show you what we got the rat to do. Okay. While it's on this carousel, this is sped up a little bit. The rat is running around. These areas are color-coded for us to see, but this rat has learned to not go into the red area because its feet will hurt. There'll be a mild shock. It's also learned not to go into this blue area. Its feet will also hurt because there's a mild shock there, and it learns to navigate both of these spatial frames, and we were able to decode what the rat was thinking about moment to moment as we did this. So this is a rudimentary form of mind reading, if you will. I'm going to try and show you a more a live version of mind reading. I'm going to invite a couple of colleagues of mine to come out, if you will, please. Okay. This is Dr. Ahmet Omortag, who works with me, and he's going to provide a brain. Okay. And Dr. Samah here is going to act as a physician. He's in fact a physician. And I'm going to, well, I'll describe what he's doing. What had occurred to us as we're recording the activity in the brain is that the electronics that we had built so that we could put on a rat, okay, those electronics are not even available for recording from human brains. And the third aspect of my job that I absolutely love is I get to think about ways to change the world. So a sad story inspired me to start to record from human brains in emergency departments, in emergency situations. A friend of mine was knocked down by a FedEx truck. She hurt her head. She was in the hospital, and she was unable to receive an EEG. She was unable to have her brain examined. Okay? And it took weeks in order to do that due to various logistics and the fact that it's very difficult to record the brain's electrical activity except in very specialized circumstances. What Samah is doing here looks really gnarly, but all he's doing is he's putting some jelly, okay, salt water and jelly in essence, into this cap so that they can make a connection between the scalp and the white electrodes so that we can pick up those electrical signals. And what had occurred to me is that, look, in our laboratory, we're capable of recording the electrical activity from rats as they run around and hit their heads on walls and jump and do various things. And it should be possible to do this very same thing in the emergency department for people who need this kind of care. I'll give you an anecdote. If you remember, 2 winters ago, Natasha Richardson, the late actress, had fallen and hit her head while skiing. She subsequently died. She had visited 2 emergency departments and never had this procedure. Had she had this procedure, it's very likely the doctors would have recognized that her brain had suffered an injury and been able to treat her. So one of the very nice things about my job is that I get to do things like this, develop a technology, taking it from the laboratory into the clinic where we're able to look at the brain's activity. And what I'm going to try and show you is a little bit of mind reading again, if we will. You can let me know when we can activate this. Okay. I'm going to, can we see the monitor, please? Okay, here, Sama, if you'll, there we go, reduce the gain. This is the electrical activity coming from Ahmet's brain. It starts on this side and it's going to the other way. I'm going to ask Ahmet to close his eyes, okay, just to relax. There's a lot of noise here. If you'll open your eyes, and maybe we'll ask you to shift your eyes left and right. Sama. If you'll cause him to make lateral eye movements, don't touch him, please. This is not looking all that. There we go. So as he moves his eyes left and right, you can see these deflections here. Okay, they're very noisy, but they're there. Okay. This is the. Ahmet has, if he'll close his eyes and relax, we'll be able to see a particular signal. Okay. But I'm not sure he can relax enough for us. Okay. No one's watching, Ahmet. No laughing. Can you adjust the gain somewhat? Okay. We're looking for something called a gamma rhythm. An alpha rhythm, excuse me. Okay. Can you open your eyes? I'm not seeing it. This is, in fact, his heartbeat that we're picking up on his scalp. Okay. Okay. But Sama is not going to relax for us. So, in any case, this is the kind of thing that we are able to do in circumstances so that we can interpret a person's functional brain state and, if necessary, intervene. Can I go to the next slide, please? If you submit those data to our computer, what you're able to do is to find very often clear signals from the raw data like this that are telling us that the brain is in a functionally bad state. This is what schizophrenia looks like when the EEG is interpreted appropriately. I'm going to go to the last slide. Okay. And the last thing that I love about my job is that I get to work with a lot of very different people. This person's a biomedical engineer, this person's a biomedical engineer, this person's a biologist, this person's a biochemist, this person's an electrophysiologist, this person's a medical student, this person is a behavioral scientist,
and
this person's...
what's with all the dogs?
And I get to take my dog to the lab.
Professor André Fenton, everybody. Thank you so much.